Welcome to today's video. Today we're going to be talking about potential energy, so that's elastic potential energy and gravitational potential energy. We're going to begin with elastic potential energy. So the elastic potential energy of an object is the energy stored in an elastic material due to its extension. The equation for elastic potential energy is E equals half ke squared. We're going to show what each symbol means. E obviously is the elastic potential energy measured in joules. K is the spring constant, and that's measured in newtons per meter. We're going to talk about that a little bit more later on. E is the extension, and that's measured in meters. Usually when it comes to springs, you're not going to have meters, but you won't be extending the spring by a couple of meters. It's always going to be in centimeters, and you will have to change those units into meters. So the spring constant, it's a measure of the stiffness of a spring, and it's the force needed to stretch the spring by 1 meter. And obviously a higher spring constant, the stiffer the spring is, or the harder it is to extend. So what happens when the spring is released? So the elastic potential energy that's stored in the material, whether that be an elastic band, a spring, or whatever, and you release it, and that is transferred into kinetic energy, obviously the energy of motion. It reaches a certain speed, and this energy obviously doesn't continue to have this energy. This energy is transferred as heat and dissipates to the surroundings. It's like if you kept stretching an elastic band out and in, out and in, out and in, it would eventually warm up to hotter than it was originally. Another key thing to think about is, what is potential energy? So it's the energy stored by virtue of the object's position. So it's not, in essence, energy it has. It's energy that it could have from that changing condition. A more obvious one is the one we'll be talking about next, which is gravitational potential energy. But firstly, we're just going to do one question on elastic potential energy. So a spring with a spring constant of 16 Newton per meters is stretched by 50 centimeters. What is the elastic potential energy of the spring at full extension? So first thing we want to do, rewrite the equation. Always want to do this in your exam questions. Then we're going to write down the parameters that we've got. So K, spring constant, is obviously 16 newtons per meter, and the extension is 50 centimeters, which when transferred into the units of just meters is 0.5 meters. I'm going to plug that into the equation. Half times 16 times 0.5 squared. 0.5 squared is 1/4, or 0.25. So you get half times 1/4 times 16. So that shows that the elastic potential energy is just 2 joules. So now on to gravitational potential energy. This is the potential energy of an object by virtue of its position in a gravitational field. The equation for this is E equals mgh. E, again, obviously, is the gravitational potential energy. That's still measured in joules. M is the mass of the object, measured in kilograms. G is the gravitational field strength, and that's measured in newtons per kilogram. So the gravitational field strength is the force per unit mass acting on an object due to gravity. Now this is obviously going to be different depending on which planet you're on, star you're on. Gravity is stronger on Jupiter than it is on Earth. But this will always be given to you in the exam, so you don't need to remember any numbers. And h is the height above the surface, and that's measured in meters. So this isn't the height above the surface that, like, the person holding a ball, for example, is standing on. This is from the Earth's surface, because a person holding a ball and they're 20 meters up on a hill, the ball is still going to have that gravitational potential energy, as is the person. How is gravitational potential energy transferred? So when an object is released from a height, it's going to start gaining speed as it falls towards ground, and that means that it's going to gain kinetic energy. So the gravitational potential energy is directly transferred in the kinetic energy. This is just a diagram of 2 separate balls, same mass, but at 2 different heights, and it's different to the kinetic energy one, which is square law dependency. This is simply just, it's twice as high, so it has twice as much potential energy. Just going to do one question on gravitational potential energy. Actually 2, sorry. But so the first one, so a 0.5 kilogram ball is raised to a height of 25 meters. what is the gravitational potential energy of the ball? I'm going to take the gravitational field strength to be 10 meters. First thing we want to do, write down the equation. E equals mgh. We're going to write down all the parameters. H equals 25 meters, G equals 10 newtons per meter, and M equals 0.5 kilograms. I'm going to just simply plug this into the equation, and we're going to get the potential energy, which is 125 joules. This one's going to take a little bit more thinking, as it involves another type of energy, and we're going to have a think about that. But what is the maximum speed of a 0.5 kilogram ball? Sorry, what is the maximum speed of a 0.5 kilogram ball would reach when dropped from a height of 15 meters? Again, we're going to take the gravitational field strength to be 10 newtons per kilogram. So, which energies do we want to take into effect here? So it's going to be the gravitational potential energy and the kinetic energy. Now, we're going to assume that all the gravitational potential energy is converted into kinetic energy. Obviously, this wouldn't happen in a perfect world. There's wasted energy, etc., etc. But that means that the kinetic energy is the same amount or equal to the gravitational potential energy. So we are going to equate those sums. mgh equals half mv squared. So one key thing that we can see there is that m appears on both sides. So it's essentially useless in this equation. So we can cancel that out when we rearrange it, which we are going to do. We're going to rearrange for v, or speed. So that gives us v equals the root of 2 times gravitational field strength times height. And from this, we just simply plug in the numbers, and we get 15.8 meters per second.